Number 1, write a function to represent each of the following. Kareem sent a chain email to 10 of his friends. The number of people who got the email increases by a factor of 1.4 every week. Okay, so the first thing that we want to do is to remember our exponential form. So our exponential form is written as f of x equals a b to the x, or to a power. So remember, a is our initial value, b is our growth rate, and of course x is our independent variable. So looking at our first here, my initial value is 10. So I'll have f of x equals 10. My growth rate increases by a factor of 1.4 every week. So 10 times 1.4, and then to the power of x. B, again, looking for my initial value. So my initial value is a. I'm sorry, 3. And then looking at what my growth rate is, it's going from 3, and then at 1, it's at 6. At 2, it's at 12. So if I put that in table form, so 0, 3, 1, 6, 2, 12. I can see it's doubling or multiplying by 2 each time. So as a function, I'll have f of x equals my initial value of 3 times my growth rate of 2 to the power of x. Okay, C, I'll have f of x, my initial value is 5, and it might be a little harder to find your growth rate here. So I need to know how I'm getting from 5 to 8. So I'm multiplying by something, by a value here. And I'm looking for that value that I'm multiplying by. So to determine the value that I'm multiplying by, I'm going to work backwards. And I will divide. So 8 divided by 5 gives me 1.6. And I'll check that value, make sure that 12.8 divided by 8 gives me the same. And it also gives me 1.6. So my growth rate would be 1.6 to the exponent x. D is a decay, so I know my growth rate is going to be between 0 and 1. I have an initial value of 4, so f of x equals 4. And building my table, I have a value of 0, 4, and then I have one of 1 and 2. And it's kind of hard to tell from that point, but already I can see that it's multiplying by half. So 4, 1/2 to the power of x. And E, my initial value, is 6. So f of x equals 6. And from 6 to 1.5, I'm multiplying by 1/4. I could check that value and make sure that I'm multiplying by 1/4 for each of them. 6 times 1/4 to the power of x. Number 2, identify the key features of each of the functions. So A, I'm answering growth or decay. I can see that it's increasing from left to right, so that is a growth. My y-intercept, or initial value, is 1. The domain of the function is all real numbers. Or remember, we can also write that as negative infinity less than x less than infinity. The range of the function, I can tell that since it is an exponential function, it is approaching 0, but will never reach 0. So y is greater than 0. And the asymptote is here along my x-axis, so that would be y equals 0. B, I can see that this is a decay because my growth rate is less than 1. The y-intercept is my initial value, which is located right there, which is 32. The domain of my function, if this was graphed, is all real numbers. Again, I can write it as negative infinity less than x less than infinity. The range of the function, again, is y is greater than 0. And again, the function has an asymptote at y equals 0. And I could verify all of this by graphing it in my graphing calculator. So there are currently 1,250 bacteria in a sample. The number of bacteria decreases by 8% each hour. The function models the number of bacteria after 6 hours. So my y-intercept is 1,250. It says it's decreasing, so it's a decay. The domain of the function, I think for this situation, because of where the graph would begin, that my domain, my least domain, is 1,250 less than or equal to x. And it can go as great as infinity, so less than infinity. Or I could say x is greater than or equal to 1,250. The range of the function, okay, I actually think that I got this mixed up here. Let me redo that one. Sorry, haven't quite woken up this morning, so let me fix that. That would actually be the range of my function. Okay, and actually I think in the situation, we're still gonna have an asymptote at 0, so y equals 0. And the domain of the function is going to be all real numbers. Or just depending on the situation, I would accept 0, x is greater than 0. or equal to 0. Just thinking about the situation, and it could be x is greater than or equal to 0. That's acceptable. Okay, the range of the function. I would accept two things here too. I would accept that y is greater than or equal to 1,250. But that would kind of change our asymptote, which we don't really deal with in the 8th grade, which is what made me question that there. So really, it should be all real numbers, probably for this situation. So y is greater than 0 is what we should have probably. Okay, D, this is a decay. The y-intercept is 1. The domain is all real numbers. Again, can be negative infinity, less than x, less than infinity. The range is y is greater than 0, or all numbers greater than 0. The function has an asymptote at y equals 0. Okay, number 3, based on the data, make a reasonable prediction for the value of the used car after 12 years. So looking at my graph, I am going to make a reasonable function for my graph. So my initial value is 5. And the next really great value I could see is 4, but I'm going to go ahead and go to 1 and start collecting some of that. So 1 is at 4. 2 looks like it is at 3.2. Remember, these are thousands, so this is really 5,000, and this is 4,000. And this would be like 33,200. And 3 looks like it's at 2,500. And 4 looks like it's at 2,000. So I'm looking at a growth rate, a reasonable growth rate. So I'm going to look at a couple of them. So let's first get the first one between 4,000 and 5,000. And that one is 0.8. And then looking at from 3,200 or 3,200, see our growth rate there again is 0.8. And I can keep going, but it looks like already that 0.8 is probably the best growth rate for my data here. So I'm going to begin to write my function f of x. My initial value is 5,000. My growth rate is 0.8. And I want to know 12 years, so I'm going to type in that information into my calculator. Okay, when I type that information in, I get 343.59 or 0.597. So I might round and say 343.60. So it would be $343.60. So I put $1,000. Really, that's probably not appropriate there. It's $343.60 because it's decaying. So if I want that in thousands, I could divide. That would be $0.34,000. So that is acceptable as well. Okay, place an X in the box to indicate if you agree or disagree with each statement. Provide justification for your response. So be careful reading through these. They're a little tricky. I've done them already. Um, so just be careful because they are a little tricky. The population P of a town after T years is modeled by the function P equals 23,900. Okay, so the first statement, the population of the town is decreasing 3.75% each year. While looking at my function, I can see it says 1.0375. So it's actually been added on to 100%. And if I add to 100%, or you can just see if my growth rate is larger than 1, that it's actually going to be a growth, not a decay. So I disagree. 1.0375 would result in a growth. Okay, so each year the population increases by the same amount of people. Again, I disagree because that's the difference between a exponential and a linear. It's not increasing by the same amount of people. It's increasing by a rate, so a percentage. So it's actually the number of people each year will increase. The graph of the function modeling the population of the town has a y-intercept at the point 0, 23,900, which represents an initial population of 23,900 people. And this I agree with because we can see it's right here in my function, my initial value. So we could say it's the a value in the function, whatever makes sense to you in this situation. Okay, B, Ray purchased a used car for $9,185. Each year it depreciates 9.5% in value. Okay, so the value of Ray's car after T years can be modeled by the function P equals 9,185. I disagree. It says it depreciates, so I need to be decaying, and this would not result in a decay. So we need to make sure that um, it needs to decay. So we want to do 1 minus 9.5. So our function would change here in those parentheses. So it needs to be 1 minus, actually, sorry, fix that. It needs to be 1 minus 0.095. Okay, the graph of the function that models the situation has an asymptote at y equals 0. I agree with this. It would never actually reach 0. So the car would start at 9,185 and never actually reach there. Never reach a value of $0. The value of Ray's car decreases by approximately 873 each year. Well, I disagree because we know that it's not going to depreciate by the same amount each year. Um, it will be different each year because it's exponential. So at first it'll be a lot, and then as it slows down, thinking of my graph, it's not going to depreciate quite as quickly because the percentage would be less at that point. C, 9 times 2/3 to the x power. The function represents exponential decay at a rate of 33 1/3%. Okay, so the function represents exponential decay at a rate of 33 1/3%. I'm sorry, I had to go back and refresh my memory on that one. 2/3, if I look at my function, it's 0.6 repeating, which is 66 and 2/3%. So if I think of this as a percent of decrease, that would represent 1 minus, or 100% minus 33 1/3%. That would get me my 2/3%, or my, I'm sorry, that would get me my 2/3 or my 66 and 2/3%. So I agree with this. 100% minus 33 1/3 equals 66 and 2/3. So, okay, the range of the function is all numbers greater than or equal to 0. I agree. Okay, and f negative 3 equals 30.375. So if I want to look at the value of negative 3, I'll take 9 2/3 to the negative third power. Okay, sorry, I'm going to back up a little bit. I said this was I agree, but that's not correct. I need to fix that. I knew there was something off with that equal to. This is what I get for doing this early in the morning. Y is greater than or equal to 0. It can't be equal to. I disagree. The asymptote of y equals 0. There will be an asymptote of y equals 0. The function will approach 0, but not reach it. Okay, looking on the last one, if I typed this into my calculator, 9 2/3 to the negative third power, we would get that value. So I verified with my calculator. Okay, D, the graph below represents the exponential decay. The first statement, the graph represents the function 12, so my initial value 12, I agree, 0.75, and is decreasing at a rate of 75%. Okay, so let's set up a table of values to examine my growth rate. So my initial value is 12. My first value looks like it's 9. My second value looks, well, let's skip a little bit. Let's see, my second value is kind of hard to see, but my third value is at 5. But just between 12 and 9, working to find my growth rate, I get 3/4. So it's multiplying by 3/4, just like my function says. But that means it's not decreasing at 75%. It's actually decreasing at 25%. So I'm thinking of what's been taken out of my whole of 100%. Well, that's 25%. So I disagree with this. So 100 minus 25 is 75%. The graph of the function has a horizontal asymptote at y equals 0. I agree. The line is approaching but not reaching. The value of the function when x equals 0, when x equals 0 is 12. That would be my y-intercept, 0, 12. Okay, so I agree. It's the initial value. Okay, for each geometric sequence, identify the first term, the common ratio, and list the first 5 terms. Okay, so my first term here is 48, and my common ratio is half. So I'll have 48, 24, 12, 6, and 3. Okay, my first term is 5. My growth rate, or my common ratio, is 2. So I'll have 5, 10, 20, 40, and 80. Okay, my next one, my first term is -2. Common ratio is 3. Okay, so I'll have -2, -6, -18, -54, and -162. Okay, my next, I can see my first term is 1/2. Common ratio is 2. So I'll have 2, 1, 0.5, 0.25, and 0.125. Oh, I'm sorry, I did that backwards. Let me fix that. Again, early. Should not be doing this early. Okay, my first term is half, and it's doubling. So 1, 2, 4, and 8. Okay, and last, my first term is 100. Common ratio is half, 100, 50, 25, 12.5, and 6.25.